Chapter 5. The Time Value of Money. We need a way to reduce future cash promises into an equivalent number of today's dollars or vice versa. How do we make this equivalence? We look at the opportunities available to us in the capital markets. For example, let's walk into a local bank, deposit some money, and see what happens. Deposit $100 today. Close account in 1 year and receive $110, which consists of $100 principal returned plus $10 interest. We have $110, the future value at the end of year 1. We represent it by the symbol FV1 equal to $100 principal returned plus $10 interest equal to $100 principal times 1 plus 10%. $100 principal is the value today. We represent it by the symbol PV0. 10% is the interest rate. We represent it by the symbol I. We arrive at the following formula. Future value at the end of year 1 is equal to present value today times 1 plus interest rate. How about letting us turn the question around? We ask, what deposit yields $110 next year? That is, we ask, what is the present value of $110? From our earlier discussion, we know that future value at the end of year 1 is equal to present value today times 1 plus interest rate. Dividing both sides by 1 plus I, we arrive at the following formula. Present value today is equal to future value at the end of year 1 divided by 1 plus interest rate. Let us extend the 1 period future value and present value results to any number of periods. For example, deposit $100 today and close out in 2 years at the end of year 1 by formula. The account balance will be the present value today times 1 plus interest rate, represented by the symbol FV1. At the end of year 2, the account balance will be the account balance at the end of year 1 times 1 plus interest rate equal to the present value today times 1 plus interest rate raised to power 2, represented by the symbol FV2. Now, if we don't close out the account in 2 years, but in 3 years, then at the end of year 3, the account balance will be the account balance at the end of year 2, represented by FV2 times 1 plus interest rate equal to the present value today times 1 plus interest rate raised to power 3, represented by the symbol FV3. Generally, the future value at the end of period N is equal to the present value today times 1 plus interest rate raised to power N. Dividing both sides by 1 plus interest rate raised to power N, we arrive at the present value formula. The present value today is equal to the future value at the end of period N divided by 1 plus interest rate raised to power N equal to future value at the end of period N times 1 divided by 1 plus interest rate raised to power N. Bonus: what scenario will make future value at the end of period N equal to the present value today? By looking at the formula, we see that this could happen if the interest rate is 0. Now, from formula in previous slides, we multiplied the present value today by the multiplier 1 plus interest rate raised to power n to obtain the future value at the end of period n. So we call this multiplier the future value interest factor. We multiplied the future value at the end of period n by the multiplier 1 divided by 1 plus interest rate raised to power n to obtain the present value today. So we call this multiplier the present value interest factor. Now, this slide summarizes the information of using TIBA2 Plus or TIBA2 Plus Professional. This slide provides an example of calculating the future value by using the future value formula and the financial calculator. Simple interest is the interest paid on the principal sum only. Then the future value at the end of period n is equal to the present value today plus interest accrued, which is only paid in principal, equal to the present value today times 1 plus interest rate times n. Note, for the compound interest, interest is calculated on the initial principal and also on the accumulated interest of previous periods. So the future value at the end of period n is equal to the present value today times 1 plus interest rate raised to power n. For simple interest, the investment result for n periods is given by this formula. For compound interest, the investment result for n periods is given by this formula. We see that if the investment horizon lengthens, given the same interest rate, the investment result from compound interest is larger than the investment result from simple interest. The following provides you with a numerical example to show that the difference in the investment results from compound interest and simple interest increases as the investment horizon increases. If the investment horizon is for 1 year, we see that the investment result from the simple interest and the compound interest is exactly the same. If the investment horizon is for 2 years, we see that the investment result from the compound interest is larger than the investment result from the simple interest by this amount. If the investment horizon is for 3 years, then the investment result from the compound interest is larger than the investment result from the simple interest by this amount. Why do we want to find out the interest rate? Because we may want to find out the rate of return earned for the investment opportunity. For the simple present value and future value problem, we can easily find out the interest rate by either using the formula or the financial calculator. Why bother calculating the number of compounding periods? Because we may want to find out the investment horizon needed, payback periods, etc. For the simple present value and future value problem, we can solve the number of compounding periods by using the formula presented here. Of course, we can solve it by using the financial calculator. We next are going to discuss future value and present value for different cash flow patterns. Annuity. Annuity represents payments or receipts of equal cash flows per period for a specified amount of time. Ordinary annuity is the annuity in which the payments or receipts occur at the end of each period. Annuity due is the annuity in which the payments or receipts occur at the beginning of each period. The upper panel gives an example of future value of an ordinary annuity. The future value is the sum of future value of each annuity payment. The lower panel gives an example of future value of an annuity due. The future value is the sum of future value of each annuity payment. Now, for the upper panel, if we multiply the future value of each annuity payment by 1 plus 6%, we will get the same result as shown in the lower panel. We conclude that, given the same interest rate and the same number of periods, future value of an annuity due equals future value of an ordinary annuity times 1 plus interest rate. For the future value of an ordinary annuity, we can calculate it by the formula annuity times future value interest factor of an ordinary annuity. We of course can solve it using the financial calculator. Note, the annuity payment is input under the variable name PMT. For the future value of an annuity due, we can simply treat it as an ordinary annuity problem and multiply the future value of an ordinary annuity obtained by 1 plus interest rate. The upper panel gives an example of present value of an ordinary annuity. The lower panel gives an example of present value of an annuity due. By simply looking at the graphics shown here, we observe that for the present value of an ordinary annuity, the present value of each annuity payment is discounted for one more period compared with the present value of an annuity due. We conclude that, given the same interest rate and the same number of periods, present value of an annuity due equals present value of an ordinary annuity times 1 plus interest rate. For the present value of an ordinary annuity, we can calculate it by the formula annuity times present value interest factor of an ordinary annuity. We of course can solve it using the financial calculator. For the present value of an annuity due, we can simply treat it as an ordinary annuity problem and multiply the present value of an ordinary annuity obtained by 1 plus interest rate. Marlene wishes to provide for the college education of her daughter. Her daughter will begin college 5 years from now, and Marlene wishes to have $15,000 available for her daughter at the beginning of each year in college. How much must be invested at a 12% annual rate of return in order to provide the 4-year $15,000 annuity for her daughter? We solve this problem in 2 steps. First, step forward to the end of year 4, and then we look forward. We can summarize the future 4-year $15,000 annuity into one equivalent value at the end of year 4 easily by solving the present value of an ordinary annuity. Here we show how to solve it by using table or financial calculator. Second, The value we just obtained from the step 1 is the equivalent value of the 4 future annuity payments, so we can disregard all those 4 future payments. Our problem then becomes one future value at the end of year 4, and we want to find out the present value given the interest rate 12%. Here we show how to use table and financial calculator to obtain the result. Perpetuities. Perpetuities is the uniform cash flow occurring at the end of each year forever. The present value of perpetuity is equal to the equal cash flow divided by the interest rate. This is the formula we apply to obtain the price of the preferred stock or perpetual bond. Present value of an uneven payment stream is obtained by summing up the present value of each payment. Suppose you want to compare two investments. One investment promises an annual return of 10% compounded annually. The other promises an annual return of 9.92% compounded quarterly. Is there some way to compare the two investments? Yes. How? We should calculate the effective annual rate of return. The effective annual rate of return is calculated by 1 plus the nominal annual rate of return divided by the number of compounding intervals per year raised to the number of compounding intervals per year minus 1. What is the annual effective rate if the annual nominal rate is 8% compounded quarterly? We can apply the formula to obtain the answer. When applying the formula, the annual nominal rate is 8%. The number of compounding intervals per year is 4. Your monthly statement from your bank credit card shows that the quarterly rate of interest is 1.5%. What is the annual effective rate of interest you are being charged on your credit card? We can apply the formula to obtain the answer. When applying the formula, the number of compounding intervals per year is 4. Be careful, 1.5% is the quarterly rate, so you should not divide 1.5% by the number of compounding intervals per year, which is 4 in this case. Net present value of an investment is calculated by present value of future cash flows minus initial outlay. One should undertake the investment if and only if net present value is greater or equal to 0. We will work on some practice problems. Suppose I buy a car and the terms of the loan call for 3 equal end-of-year installments of $4,000. Assuming that the interest rate is 10%, how much am I paying for this car? I would recommend you to always draw cash flow timeline for the time value of money problem. By looking at the cash flow timeline, we have the question mark located at the very beginning. We have equal cash flows at the end of every year, so this is the present value of an ordinary annuity problem. This slide summarizes the information we have and the value we want to solve. This slide illustrates the solution by using the formula and the financial calculator. You would like to purchase a new car. You believe that the model you want will cost $18,000 in 4 years. How much would you have to deposit in a bank account today at 5% interest in order to have $18,000 available to you 4 years from now? First, draw the cash flow timeline. By looking at the cash flow timeline, we have the question mark located at the very beginning. We have one lump sum value at the end of year 4. So, this is a problem of present value of a given future value. This slide summarizes the information and the problem to solve and provide the solution by using formula and financial calculator. Joe plans to put $3,000 each year into an account for 3 years at 8% compounded annually. What is the balance at the end of year 3? First, draw the cash flow timeline. By looking at the cash flow timeline, we have equal cash flows at the end of every year, and we have question mark located at the end. So, this is a future value of an ordinary annuity problem. This slide summarizes the information and the problem to solve and provide the solution by using the formula and the financial calculator. You want to create an endowed chair position at A&M Commerce for $150,000 per year into perpetuity at 5% interest rate. How much should you donate? This is a present value of a perpetuity problem. The present value of a perpetuity is calculated by the equal cash flow divided by the interest rate. The equal cash flow for this problem is $150,000. Interest rate is 5%. You borrow $5,000 to purchase a computer. The loan is to be repaid in 5 equal annual end-of-year installments. The interest on loan is 9%. What is the loan payment? First, draw the cash flow timeline. By looking at the cash flow timeline, we have $5,000 at the current period, and we have question mark located at the end of every year. So, we want to solve the payment. This slide summarizes the information and the problem to solve and provides the solution by using the formula and the financial calculator. We next want to construct the loan amortization table for this problem. This is a loan amortization table. For each period, the interest payment is calculated by beginning balance times interest rate. The principal repayment is calculated by the loan payment less the interest payment. The ending balance is calculated by the beginning balance less the principal repayment. We observe that the amount of interest paid is decreasing every year, and the amount of principal repaid is increasing every year. George plans to retire in 5 years. he would like to deposit an amount each year during his remaining working years that would guarantee him a $30,000 annual retirement income supplement for 20 years. The interest rate is 5%. First, draw cash flow timeline. By looking at cash flow timeline, we have the question mark located at the end of every year for the first 5 years. We have $30K at the end of every year for 20 years, starting from the end of year 6. We want to solve the payment. By looking at the cash flow timeline below, we solve the problem in 2 steps. First, we step forward to the end of year 5 and convert $30,000 annuity to a lump as of the end of year 5 by the present value of an ordinary annuity. We denote the value obtained as L. We then find the payment in forms of an ordinary annuity with the future value being the value of L just obtained. This slide shows how to obtain the value of the first step by using the formula and the financial calculator. This slide shows how to find the payment after obtaining the value at the end of year 5 using the formula and the financial calculator. The interpretation of the payment number we just obtained. We now present a net present value example. We illustrate how to use the financial calculator to obtain the net present value in detail in next slide. We first draw the cash flow timeline. We then show you how to use TIBA2 or TIBA2 Plus Professional to calculate the net present value in detail.